Thank you for joining for quick lunches. We will have more time in the coming weeks, so thank you for agreeing to the tighter schedule the first 2 days. Next up, we have a talk on minrank, which is a very hard tensor problem, and we'll have Takunari Miyazaki giving us a talk from Trinity College. Thank you.
Thank you, James. James and I have been working on a project to count the number of non-singular objects, bimaps or distributive products to be more precise. And this has led us to study the complexity of testing singularity of bimaps. So it's in this context that we became interested in minrank, which arose as one of the most basic problems in our study. So I'll start with a more kind of a practical definition of a problem. So let's say R is a ring, and you're given L+1 matrices. These matrices need not be even square. So what we're looking for is elements in a ring that minimize the rank of this linear combination. Or perhaps you have some target rank and you're trying to find a sum that is below that target. So as far as I can find out, this first arose in a context of practice in the cryptanalysis of what's called hidden field equations protocol by Kipnis and Shamir. This Shamir is the same Shamir from RSA. Their analysis, cryptanalysis, was improved by Nicolas Courtois a few years later. And he studied, Nicolas Courtois, he studied this minrank in great depth. Actually, this was one of the main topics in his PhD dissertation. And he also proposed, based on his deep understanding, zero-knowledge authentication. But then several years later, using Grosvenor bases, some efficient solutions were found. But these are also all done in a context of cryptography, rather than a very rigorous complexity analysis. Now, complexity theorists often prefer to study or state problems in a decision form. So let's consider minrank in the following decision form. In fact, I'm putting in the underlying ring as part of the problem definition. So given L+1 matrices and target rank R, integer R less than equal to M, are there elements in the underlying ring such that the rank of this linear combination is at most R. For integers, this is actually undecidable. The proof is essentially a reduction from Hilbert's 10th problem, which I think is the solving Diophantine equation. So it's undecidable. But for fields, basically all fields that we are interested in, all fields that arise in practice, for those fields it's NP complete. And this is all summarized in this paper by Bus, Franzen, and Shalit in 1999. What I like to do is to spend first half of this talk at least going over this Bus, Franzen, and Shalit's result on finite fields. So let's start with this assumption. In fact, this is not really a requirement, but this is something that James and I felt that it might simplify things in the context of our work. But the NP completeness result doesn't require this assumption. But I'm just going to put out this there anyway. So the field is fixed and input size is proportional to the number of non-zero entries. And NP completeness of minrank follows from that of this problem called a singular matrix. So here, so I'm stating this for the finite fields where I'm putting in Q as part of the problem definition here. So, Q being a constant, so you have a problem for each field. So here we are given a matrix defined over a finite field of order Q with some variables. Let's say L variables, x1 through xl. And so you ask, are there field elements that, so you plug in those field elements into these variables, and that makes the matrix singular, or determinant 0. So this problem was essentially proved to be NP complete in a context of algebraic complexity theory by Valiant in 1979. Now, Valiant did not exactly prove this theorem, or perhaps he didn't really care. So this Valiant 79 refers to his famous stock paper titled Completeness Classes in Algebra, which is one of my favorite papers, in which he develops a basic machinery to define algebraic analog of P and NP, now called VP and VNP. So it's in this context that he basically builds this machinery, and I mean the proof is all there. So to prove this, first so it's an NP completeness result. So typically, we try to reduce from SAT or other well-known NP complete problem, but this can be done from SAT. So SAT is the Boolean satisfiability problem. So the first step is to reduce SAT to this problem we call affine variety. So you're given a multivariate polynomial f with L variables, and you ask whether there is a 0 for this polynomial. So this ZF is the 0 space in the affine space of over FQ. So how do we do this reduction? So given a formula, let's say in a conjunctive normal form, somehow construct a polynomial f phi such that formula phi is satisfiable if and only if f phi has 0. So this is done by what is now called arithmetization. Again, Valiant didn't call this technique arithmetization, but this is a very important technique in complexity theory where somehow you map a Boolean formula into an algebraic polynomial. And it's done recursively in the following way. So the base case, so phi is a Boolean formula, so the base case is phi has a single variable. In that case, you let g phi to be x to the q minus 1. If phi is a negation of a Boolean variable, then you let g phi to be 1 minus x to the q minus 1. Now, in a finite field, x to the q minus 1 is 1 if and only if x is not 0. So this is turning false into 0, 1, sorry, no, turning false to 0, true to 1, right? Otherwise, phi is composed from disjunction, conjunction, or a combination of the two. So if phi is formed from a disjunction, then let G phi be G phi 1 plus G phi 2 minus G phi 1 times G phi 2. This is a simple exercise to show that equivalence. If it's formed from a conjunction, then you simply multiply two polynomials. So this is mapping false to 0, true to 1. But we're looking for 0, so we need to flip this G phi to flip 0 to 1, 1 to 0. So define F phi to be 1 minus G phi, and this does it, right? Okay. Now, so this shows that affine variety is NP-complete. So now we're interested in reducing affine variety problem to a singular matrix, and this also involves another very important technique called cycle covers. So I would like to go over a little bit how this works. So first we call this, well, this is a standard definition of a determinant, nothing special. But from this, you can think about problems involving graphs. So let gamma f be a directed graph. This is in fact a complete directed graph on vertices 1 through n, each of whose edge has weight mij, including 0. This is a complete graph. Then each permutation may be identified by a cycle cover of this graph. So each permutation can be expressed as a product of disjoint cycles, and that disjoint cycle can be identified by a cycle cover of this graph. Now, if you have, let's say, a directed graph with some cycle covers, and if it consists of only length cycles, then the sum of the products of the weights of all cycle covers corresponds to G's determinant. To be more precise, the determinant of G's adjacency matrix. So using this observation, Valiant translated polynomial to determinant problem, again, recursively. So given a polynomial, we first construct a directed acyclic graph, gamma f, with a source S and a sink T recursively. So acyclic means that there's no cycle. In fact, there will be a cycle later, but first we can construct this graph with a source S and sink T in the following way. So again, this is done recursively. So the base case is, so f has a single variable. In that case, let gamma f be a directed path of length 2 with weight x followed by 1. If f has a single field element, same thing, directed path of length 2 with weight alpha and then followed by 1. So just a simple path of length 2. If f is negative f1, then you simply use gamma of f1 followed by a directed edge of weight 1 at the end. From S, you add this one additional edge. If f is a product of two polynomials, then gamma f is simply gamma f1 followed by gamma f2. You just glue them together. If f is a sum of two polynomials, then gamma f is gamma f1 and gamma f stacked together, sharing the same source and a sink. And finally, so this completes the construction of gamma f as a cyclic directed graph. But finally, add a directed edge from T to S. So now you're introducing a cycle. And self-loops to all vertices other than the source, all having weight 1. So this is to make this graph have cycle covers of, with cycles of odd length. So that's the reason why you have this additional trick at the end. Okay, so in such gamma f, then every cycle cover is going to consist of a single cycle of odd length greater than or equal to 3, going through S and T, and then you have these additional self loops. So if you let M be the adjacency matrix of this gamma f, where each entry in the matrix is the weight of the edge ij, or if there's no edge, you put 0. The determinant is simply equal to f. In fact, the 0 space is non-empty if and only if there are field elements that makes this matrix singular. So this is the reduction from affine variety to a singular matrix. Reduction from a singular matrix to mean rank is actually fairly simple, so I'll just leave this as an exercise. It's not an open problem. So this is a very, I really like the proof, and I think it's something that's worth talking about. So I want to next spend some time, I only have a little more than 10 minutes, but going over some of the applications. I have to start with a disclaimer. I'm not an expert in security, so this is based on my recent reading on those papers. It's likely to have some errors, but I did learn something new, so I enjoyed reading them. Okay, so let me just first start with this Kipnis-Shamir's attack, which is, I think it's fairly known in the security community. This hidden field equations protocol was proposed first as one of the earliest post-quantum cryptography as an improvement to Matsumoto and Imai's scheme based on quadratic forms in late 80s. So it's post-quantum in the sense that it doesn't rely on discrete log nor integer factorization. So here's a basic setup. So you start with a finite field of order Q, and then K be an extension of degree M with an isomorphism phi from big K to little k to the n. And then consider this polynomial defined over big K, where each coefficient is randomly selected from K, and R is a small constant. And for simplicity, we assume that it's homogeneous. Now, so this is being defined as a way to define cryptography. So it's important that we can efficiently evaluate this polynomial. So this R being small is actually extremely important. They even propose that R should be no more than like 13. So and Q should be also pretty small, like 2 or 3. N they recommend like around 128. With N128 and R13, the degree of this polynomial P is roughly 8,000. Okay, and in addition, randomly select 2 invertible matrices of dimension n over little k, and then define this polynomial G so I'm kind of abusing this notation here, but so one has to conjugate by this isomorphism, and then apply S and then P and then T with this phi conjugating. So this is the, let's say, preparative setup before setting up keys. So this HFE cryptography is defined by these two sets of keys. So it's a public key cryptography, right? So you have a private key and then a public key that is, that is consistent with the given private key. So the polynomial P, S, and T are kept to the recipient, and then the public key is released in a form of this G with this field element conjugating. So this is defined over the ground field little k. So it's a set of n-homogeneous, in fact, these polynomials defined over a ground field k, it's actually quadratic polynomials in n variables. So a message is encrypted in this way. So message has n components, and then you plug in for each polynomial G1 through Gn. And this was proposed by Pattering in 96. In roughly 3 years after they proposed, this was broken by Kipnis and Shamir, or I should say weakness was exposed. They observed that when you lift these two matrices S and T, or T inverse, for technical reason, I mean, we're interested in T inverse, there are linear combinations of variable x. In fact, having expressed S and T in this form, you can simplify G to be simply SPT. In fact, G can be expressed over the big field K in this quadratic form looking type expression. From this G, so these coefficients elements in the big field, you can form a matrix G. So this matrix G is formed from these coefficients, and then they define some tricks. So here's the trick. Let G star to the k denote the matrix obtained from G, raising each entry to the q to the kth power, and then rotating all rows and columns for k times. And then consider this linear combination, where this little t is actually coming from this t here. And so it turns out that the rank of this G prime is at most R. So they make a point that so this T can be recovered by finding these coefficients that makes this G prime less than or equal to R. So this G is actually something that you can construct from a public key. So it's enough to simply, so here we have a minrank problem. I mean, you're looking for linear coefficients, little t, that makes a G prime whose rank is less than or equal to R. Now, in practice, R is a very small constant. And in fact, the equations that arise are quadratic or close to quadratic. And under those constraints, they reduce this to simple linear algebra over little k. Simple linear algebra basically means here Gaussian elimination. T can be recovered, and then from this T, using a similarly simple technique, simple in a sense that the computation is fairly simple, you involving Gauss elimination, keys SP then follow. Yeah, so this is kind of a snapshot of Kipnis-Shamir attack, which I learned that it's quite well known in security. Okay, so I mentioned earlier that Nicolas Courtois improved this Kipnis-Shamir attack, and he studied minrank in great depth. In fact, it was Nicolas Courtois who called this problem minrank, and he really, tried to sell this problem being really important. And in his dissertation, so based on his deeper understanding, he proposed zero-knowledge authentication. So I won't have time to go over all the details, but perhaps I should, let's see. So what is zero-knowledge proof? So this is a very watered-down, simple definition. I'm trying to kind of present the most basic ingredients. It's an interactive proof for prover P to convince a verifier V some statement S, but do so without exhibiting anything other than the fact that S is true. Okay? Such a proof must satisfy the three main properties. One is completeness, meaning that when S is true, then prover has to convince V to accept S with high probability. So this is for when S is true. But also, it needs to be sound in a sense that when S is false, then V has to reject S with high probability, so that false prover's claim is going to be rejected with a high probability. And then in addition, nothing has to leak out, right? The V learns nothing, the verifier learns nothing from the interaction other than the fact that S is true. So in the interest of time, I think I'm not going to go over details, but so I'll just explain what Courtois did. What he proposed was a zero-knowledge proof for minrank, and I'm giving a simplified form of minrank here. So in a original version, you also had M0. So when you asked for the rank, you had M0 without coefficient, and then alpha 1, M1, alpha L, ML, less than or equal to R. But for a technical reason, I'm dropping M0. So with that, I guess we have to be asking whether there is a non-zero coefficients, right? That makes the linear combination less than or equal to R. So in this zero-knowledge proof, the prover knows a solution for minrank and tries to convince the verifier that he's honest, that he has a correct solution without revealing the solution. Solution here in this case is the elements in the field. Okay, so so this is, I mean, the point here is that he came up with a fairly simple protocol, which if one spends about like an hour, you can understand what's going on, provided that you understand the definition of a zero-knowledge proof. So I'll just skip this. So I want to conclude this with a couple of points here. So the Kipnis-Shamir attack works on instances of minrank in which the target rank is pretty small. because in practice, he has to work with a small exponent in order for this protocol to work fast. But there's also additional constraints arising, namely that most of the equations that arise are quadratic. And it's for that reason that they were able to come up with a very effective attack. And I had mentioned this at the beginning as well. A Grosvenor basis approach has been shown to be effective on instances of main rank as well. But in this case, when the core rank, R prime, which is n minus r, is a small constant. So this is also done in a context of cryptanalysis. But I couldn't tell what they really mean in a context of rigorous complexity theoretic statement. So I would like to end this with this question, which may not be open. I mean, perhaps they already proved this, but is mean rank in polynomial time when target rank R or core rank is bounded by a constant? I'll stop here.
Do you even know, like, for mean rank 1?
I really haven't thought about it. Yeah, I don't know. But what I can tell is that right. So NP completeness reduction. I mean, going back to this Valiant's cycle cover and this arithmetization. I mean, the rank is definitely going to be pretty high. Right, so I mean, you're not going to get an NP completeness result. I mean, a reduction rather with a bounded rank.
I have a question. I find the subtlety here is that the reduction is also not just to a polynomial, but to a polynomial formula. Mm-hmm. Are they careful about that?
Are they as
the actual length of the polynomial is the length of the polynomial formula?
I mean, again, I don't want to sound too critical, but they have a very different way of, stating things, and again, I mean, their main point is to expose weakness of those protocols that are proposed being right. I mean, the post-quantum practical crypto system, and
But for those of us who want to use this as isomorphism invariance, we'd really like to know the actual complexity because we're using it.
Yeah.
NP completeness result is very careful, but these I don't.
Yeah. No, I mean this. And Courtois, I mean he's, for example, I mean, this zero knowledge stuff, which I couldn't get to really talk about. I mean, this is a very, I mean, he proved this, or he claimed to prove this. I mean, that the full proof is not in the paper, but this Kipnis-Shamir attack, which I think has been highly credited, is very, what's the right word? I mean, they come up with a very original tricks, and somehow, I mean, it was difficult for me to really accept that this was being reduced to simple Gaussian elimination, but they did it, right? But with like under certain constraints. So even yeah, I mean, I don't know how to interpret this, right? But this Kipnis-Shamir technique has been improved, right, by Courtois and then a few others. And so maybe there's something. But because of this weakness of min rank being exposed using this Grosvenor basis approach, some people felt that perhaps min rank is just not difficult enough for a crypto system. And so I have seen recent papers where you define min rank using those grids, right, instead of matrices. And they define, for the topic of this conference, maybe it would be more appropriate. It would have been more appropriate to talk about that. But I also found difficult to understand what was happening because they again have their own vocabulary and just to translate that into what I understand, it's going to take like several weeks. So. But there is something happening in the security community. That's definitely true.
Well, let's take the rest of that and do questions afterwards, Fred, and thank you, speak.